So let's first talk about the voltage gated sodium channels. There's two gates. Okay, first of all, let me remind you what voltage gated means. A change in voltage. And I don't know if you remember, I drew this on the board a while ago, where I drew something in the membrane. All right, so this is a voltage-gated sodium channel. And I've drawn one of the two gates, okay? This is called, what I tried to draw, this first gate right here. They use purple, I use green. It's an activation gate. And I drew it closed, so that the sodium cannot get in. When the activation gate is closed, they call this the resting state. There's no action potential when this gate is closed. Okay. There's another gate. The little ball and chain you see on the picture. That's called the inactivation gate. This little ball and chain here. One thing you need to know about these channels is their kinetics are very fast. Kinetics is just describes how fast they open and close. So basically just know that these channels, they open and close very quickly. V-gated sodium channels, they open, close quickly. The reason why they close so quickly is this inactivation gate. As soon as they open, they almost are immediately inactivated. Inactivation gate, they inactivate channel, closing it. Right now, I drew the inactivation gate, that little ball and chain, open. It's open here, that gate is closed. But if you get a change in voltage, you'll open the activation gate. Okay, both gates are open in this middle frame. So what will happen is there's some kind of local current that comes on the inside of the membrane. Some positive charge, so let's say it's like over here, close. And it travels to here because the positive charge is attracted to the negative charge. And basically, it's going to change the membrane potential right here, right? It's going to flip all this. And before I kind of change the voltage here, let's look what I drew a little plus sign. In this protein right here, there's a little bit of positive charge, and it's attracted to this negative sign, and it's repelled by this positive sign. This positive like charge is repelled, correct? But when you get a change in voltage, this little bit of positive charge comes over here. This flips. Does the same thing on this side. This flips. So let me erase it and change it. This would be like that. This will be like that. And there'll be now negative here. So you've had a change in voltage. It's more positive on the inside now. And now look, this positive charge repels the positive charge in the gate, and it's attracted to, more or less, the negative charge on the outside of the membrane. Okay, so that's kind of the physics behind why the gate opens. It's voltage gated. So when you repel these two gates of the activation gate will swing up. And that'll open the gate, and that'll allow for depolarization, where it was polarized, now it's going to depolarize, the sodium influx will come in. Okay. So instead of trying to redraw the whole thing, just look at the middle frame here. That's how you open the gate. Okay. As soon as you open the gate, almost immediately you close it. In this last frame, the inactivation gate is closed, but the activation gate is still open. But it doesn't matter, because as long as one of the gates is closed, the channel is no longer permeable to sodium. Okay, so very simply, we're going to point to each frame. I'm going to ask you a question here. Is this opened or closed? It's closed because the activation gate is closed. Point to the middle frame. Is this channel open or closed?
Open.
It's open because both gates are open. The activation gate is open, and the inactivation gate is still open. Okay. Is this channel open or closed? It's closed. Which gate is closed? The inactivation gate. So what we learn is only one gate is closed for it to be closed, right? Yeah.
I was trying to ask, is there a situation where one is closed, let's say one is open and the other one is partially closed? Is it a malfunction in the body or something?
One doesn't, off the top of my head, no, I can't think of one where that would be a malfunction. Yeah.
Okay, so then is there any difference? How do we kind of recall it? Because sometimes it confuses between the voltage gated and the leak gated. I mean, what is the, what can we remember in order to differentiate between the two?
Just what opens the gate. So what opens this gate is a change in voltage. But what opens a ligand gated channel? A ligand, something binds to it. That's not a change in voltage. Right? So in this class, when we were talking about ligand gated channels, what was the ligand? It was ACH, right? It was a chemical, it was a neurotransmitter. So how you remember is just what opens the gate. Okay, that's basically the best answer for that question. So does that answer your question?
Yeah.
Okay, all right, let's move on. Next channel, voltage gated potassium channel. Well, now I've kind of talked about gates. How many gates do you see? One or two? There's just one gate. Okay, so I guess it's easier in that sense. So these open and close quickly. These close so quickly because that inactivation gate, it just shuts them real quick. Okay, but these, they respond to a change in voltage. Their kinetics are much slower. They just open slower and close slower. Okay.
Which is why
No, that's not necessarily the reason why there's so many more. But yeah, do know that they open and close slower. All right, so V-gated. So V-gated, voltage-gated. Potassium channels, they have one gate. Easy to understand. The gate's either open or closed. When it opens, you'll have some potassium efflux. When it's closed, it's just closed. Okay. So nothing much to say other than what I just previously mentioned. Kinetics are slow. Slow. Okay, so I said fast and slow. The reason why I emphasize that is I want you to connect the dots here. Okay, I can remember the fast and slow. But can you understand the fast and slow by looking at the permeability curves? This is what I really want you to understand. If a cell is permeable to an ion, that means the gates are open. If a cell is permeable to this ion, that means the gate is open. So basically, look at the yellow curve. The gates open first, and then they close. Look at the green curve. The gates don't open till here, and then they close much later. So just by the shape of the curve, we say potassium voltage-gated channels, the kinetics are slower. I mean, look at it. These open, the sodium channels, they open and close. They're inactivated by the time the potassium gates open. Okay, so that's kind of the connection you need to make with, the gates being fast or slow, opening and closing. So as we go through each phase, think about which channels are open and closed and how it's changing the membrane potential. So we talked about that. And so let's talk about the events going through each phase of the action potential, starting before you even have one, the resting state. In the resting state, that was a previous lecture. And, look at, on a graph, if you're measuring millivoltage, and, that's 0, so we'll call that negative 55 and negative 70. Give some numbers to it. Plus 30. And we're just chugging along at a negative resting potential at negative 70. This is established by the leach channels. Cells are very permeable to potassium in the condition of rest because all the potassium leach channels. And we talked about that before. About the pump, it maintains those ionic gradients so you can maintain a resting membrane potential of negative 70. So in terms of the voltage-gated channels in the axon, all the gates are closed. So I'll just write that. Gated sodium and potassium channels are closed. The resting membrane potential is a negative 70 millivolts. Okay, so then to stimulate the cell, you have some graded potentials. you have to kind of reach threshold to get to depolarization. So prior to depolarization, kind of like step 1.5, I guess, you have to reach threshold from resting state. So if this dotted line is the depolarization that's required for this cell to reach threshold, graded potentials are required to reach threshold potential negative 55 millivolts. There's enough positive charge to open the gate. Let me see if I can do it. I usually don't use this tool, but I'll draw a positive charge. Maybe the positive charges were here. Those look like positive charges. And they're traveling this way. Positive charge has arrived to the axon hillock, the first segment of the axon. It has to come here. It has to be enough of a change to stimulate this cell. Okay, this molecule, the voltage-gated potassium channel. So let's say I'll use red for the graded potential. Let's say, did I reach it? Yes or no? I didn't, so nothing happens. This is all or none. So let's say, okay, well, let's give it a bigger boost. Try to rest. Okay, you stimulate here. Let's stimulate again. Yeah, no, not quite. Okay, so you just have to keep going until it's a big enough stimulus to reach threshold. It's enough positive charges. Well, let's try again and try to stimulate here. Okay, so let's say it's a big enough stimulus you actually reach threshold, so you have a depolarization. Step 2. Both voltage-gated channels respond. However, which responds first? The sodium. Okay, so you're going to increase capital P permeability to sodium. The permeability to potassium is still basically 0. I want to put down arrow permeability to potassium. They're both responding. It's just, remember, these respond much more slowly. So that's why the picture is accurate. This picture, where they show these are opening first, these just take a longer time to react, and the graph should make sense. So what I'm talking about here is this up spike. Notice how the yellow permeability curve for sodium goes up first, but the permeability at the same time for potassium is still 0. So they haven't opened yet. Okay. So you get this sodium influx. For depolarization, the sodium current means fast and powerful. The sodium current for the cell is the most powerful current in biology. Okay, it's a big one. They call this a self-generating positive feedback. A self-generating positive feedback. Considered a self-generating positive feedback. There are so many voltage-gated sodium channels. All it takes is for some of them to open due to this change in voltage when you reach threshold. So it's like when you have, so let me do it like this. That's a concept map. So you get some depolarization, some positive charge, and you reach threshold. So what if you open some V-gated sodium channels, well, you're going to allow more sodium influx. Increased sodium influx. Well, if you're allowing more sodium in, you're depolarizing the cell some more. Well, if you're increasing the depolarization, you're going to open some more voltage-gated sodium channels, and it just kind of feeds back on itself until you get this huge depolarization event. And so this creates this big spike. We use green to symbolize depolarization. So basically, the membrane potential starts to rise. And you would expect that it stops at zero when the cell is in true equilibrium, but it doesn't. This process is so fast and powerful, you actually overshoot equilibrium and go all the way to something like plus 30. Okay, so that's why sometimes people call this depolarization event the overshoot. Membrane potential doesn't just fall from negative to zero, it overshoots it to plus 30. Okay. All right, so the other thing in your notes, make the connection to the picture. Depolarization only refers to this side of the big spike. And sometimes we call the action potential a big spike. It actually looks like that on the graph, right? The sodium channels are open. You got a lot of permeability to sodium. And what do you say about the potassium channels? Open or close? Okay.
That eventually opens it because it's slow, right? It'll eventually open.
Yeah, that's basically gonna be the next step. All right, so let's move on from this slide and I'm done. Depolarization. Phase 3 is called repolarization. So let's make sense of why it's called repolarization. First, in your head, make sense of what polarization is. That was the condition of rest. In rest, was the inside of the cell more negative or less negative? In rest, wasn't it more negative? What was the number? Negative 70. But then you let all this positive in. So doesn't the inside of the cell become more positive? You depolarized it. You made it more positive. So now you have to repolarize it by letting the positive back out. And that will be in the form of potassium efflux. So in repolarization, well, two things happen. One, you inactivate voltage-gated sodium channels. They're inactivated. And the evidence of that, and you measure this in the lab, is the permeability curve. It drops all the way back down. Okay, so sodium channels inactivated. Well, I should say the voltage-gated ones. Voltage-gated. sodium channels inactivate. So that's why the little ball and chain gate closes. This is not a symbol. This protein has been studied. It's actually a globular form, and it acts just like that, like a plug. So you have decreased permeability for sodium. So no more sodium influx. Okay, decreased sodium permeability. I'll put P is for permeability in this lecture. I should write that at least once so you have it in your notes. And now the voltage-gated potassium channel is now open. Okay, so make the connection. Look at the green curve. The green curve, it's at its peak. Okay. The peak of sodium permeability is when the sodium channels have been inactivated. That will allow potassium efflux, and it will allow the membrane potential to repolarize to what it was before. So increased potassium permeability. Okay, so it's this event that allows membrane potential to repolarize. Let's remember, no sodium influx, you're only having potassium efflux. So how about I use a different color here? Let's see, so blue. Okay, so it's going to repolarize. I know my colors don't match the picture there, but I'll make it match on here. So when you repolarize, let's remember that, well, let me ask you, are the kinetics of the potassium channels fast or slow? Slow, very good. That means they open more slowly and they take longer to close. So they stay open a little bit longer because of their slow kinetics. So it takes a while for them to close. And so potassium keeps leaving. So you actually undershoot rest. You get more negative because more positive leaves because they take so long to close. So you actually go more negative. Kind of leads to phase 4, hyperpolarization. So during hyperpolarization, look at the sodium channels. The inactivation gate opens, but then the activation gate recloses, or it is closed again. Okay. They call this the rest state for this channel, where the inactivation gate opens, but the activation gate is closed. So hyperpolarization, negated sodium channels. Activation gate closed. Inactivation gate open. Again, this is considered the resting or rest state. That's important to know. When a cell has these V-gated channels and they're in their rest state, that's the first moment you can re-stimulate it. Okay, prior to that, you can't. When the inactivation gate is closed, you can't re-stimulate the cell for another action potential. But once it reaches this rest state, due to the gating, you can stimulate again. Okay, so V-gated potassium channels, I'll say still open. This is what is allowing more potassium efflux, and you're hyperpolarizing the membrane potential. So, I don't know, let's put a number to it. How about -90? Continued potassium efflux hyperpolarizes membrane potential to -90 millivolts. Okay. So it's down here, but eventually it'll get back to rest. Okay. Eventually, resting membrane potential will be reestablished by the action of the pump, the sodium potassium ATPase pump. Okay. Action of sodium, potassium ATPase pump returns membrane potential to your -70 millivolts. Let's do some half sheet questions. I want to point to this red thing. On your half sheet. Where I point at number 1, what kind of channel causes, there's 3 channels. There's the leak, there's the ligand, there's the voltage gating. Those 3. Which kind of channel caused that red thing? You're like, what's the red thing? You're supposed to know. What kind of potential is that? Is it rest, threshold, is it graded, action? What's the right word? The red thing. It's a depolarization. It's a graded potential. So what I'm asking you for number 1, what channel type causes graded potentials? Follow-up question for number 1. It's a yes/no question. For number 1, was threshold reached? Did you reach threshold potential for number 1. Now I'm going to point to number 2. For number 2, same question. Did you reach threshold potential? For number 2, that's a yes, no, easy answer. Number 3. I'm going to point to this. And the up thing, the green one, we call this the depolarization, dipole, or the overshoot. I'm going to ask you this question. Which permeability is greater? Which P is greater? Sodium or potassium? For number 4, I'm going to point to the other side of the spike, that blue line going down. We call that repolarization. Repole. Same question. Which P is greater? Which permeability is greater? One for sodium or potassium. Okay, so I'll give you a few minutes. Go ahead and answer those and we'll check back in. For number 1, I'm not going to go over the right answer. I want to see if you can get it. Number 2, let's answer that one though. Did you reach, number 2, did you reach threshold potential? Yes or no?
Yes.
Yes, you did. Number 3, for the dipole, which permeability is greater? Sodium. Yeah, sodium influx. The permeability of sodium is really low. Okay, for repolarization, which permeability is greater? Potassium is, yeah, so easy way to remember. Permeability of sodium is greater during the dipole and is greater for potassium for the repole. Okay, so we got that. Let's move on. Actually, let's take our break now. This is a good spot for a break. We'll watch these clips as a class when we come back. Come back in 15 minutes and we'll finish this lecture. Yes, go ahead.